So in the last video, we ended up with balancing equations. We did some examples of that. This slide here was showing us what happens when assigning a whole number of 1 to the most complicated substance doesn't work out, and then we move it up to 2 so that we can get the lowest whole number ratio for our balanced equation. So the next thing that we want to be able to do is use a balanced equation in order to figure out mass amounts of product that are going to form. So on this slide, we're kind of expressing our balanced equation in a bunch of different ways, and we'll focus on what this all really means. So here's our balanced equation. 2H2 plus O2 makes 2H2O, and we've been describing it more or less like this, right? That means 2 molecules of hydrogen plus 1 molecule of oxygen make 2 molecules of water. And then with that idea in mind, we could certainly think about values in atomic mass units to describe that. But now, rather than talking about the equation in molecules, I want to shift over and talk about it in terms of moles. And that shouldn't be a big change, right? We know that to get between molecules and moles, we just multiply or divide by a constant depending on which way we're going. So if I can talk about the equation in terms of molecules, I can certainly talk about it in terms of moles. But to add to that, now we know that from mole amounts, we can easily get into gram amounts. So that would let me be able to talk about the equation in terms of masses instead. And that's really important, right? If I'm running a reaction in the lab, I'm measuring gram amounts. I'm not measuring molecules or moles. So if I can more easily communicate with a balanced equation using gram amounts, that'll be really convenient. So having moles is a really big deal in terms of simplifying our ability to communicate with balanced equations. So generally speaking, this is what we want to focus on here. We're going to say we have this amount of a given reactant. How much of one of the products do we expect to see form in this reaction? And these types of problems, like I'm describing, those are called theoretical yield problems. So we have another one of those flow charts here that I think is also on handout 4, I believe, kind of describing what it is that we want to do. So just to describe the problem, right, we're going to start with some mass of my reactant A, and I want to figure out the mass of substance B that's going to form. And the whole idea here is that we're going to use the ratio of the coefficients of A and B in the equation to figure all of that stuff out. So in step 1, we would convert our grams of reactant to moles of reactant using the molar mass of the reactant, right? Divide by the molar mass to do that. And then in step 2, consulting with the balanced equation, we'd say for this number of moles of reactant A in, how many moles of product B do we get out? And in that way, really, our balanced equation is acting as our recipe. It's telling us how much product we expect to get out for a given amount of reactant, just like a recipe would tell you your yield of cookies or servings, whatever it may be. And then lastly, we're just going to want to convert back to grams. So in step 1, we go from grams of reactant to moles of reactant. And in step 3, we go from moles of product back to grams of product. So those two steps are kind of mirror images of each other. And then the step in the middle is just communicating based on the balanced equation. So, for example, let's say we've got our balanced equation here. C6H12O6 plus 6O2 makes 6CO2 plus 6 waters. And the question is asking, from 1 gram of C6H12O6, how many grams of water are we going to produce? So given amount of C6H12O6, figure out the amount of water that we're going to end up producing. So one of the first things to be aware of is there's not a direct way to communicate with the balanced equation in terms of grams, right? This equation, the coefficients are talking about molecule amounts or mole amounts. So if we're going to talk to the balanced equation, we're going to need to do that. So kind of mimicking the chart we just looked at with steps 1, 2, and 3, we're doing the same thing here. So in this chart, they're solving the problem at each step. But in reality, we don't need to do it that way, right? We can treat it just like a one-line conversion, meaning we just get our answer out at the end. But it's set up this way so we can kind of follow along with that chart that we just saw. So here's step 1, right? This is more or less the molar mass of C6H12O6, so we divide by that to get us to moles of reactant. Then in step 2, it tells me for every 1 C6H12O6, there's no coefficient, I produce 6 moles of water. So that's the balanced equation kind of acting as my recipe. And then lastly, in step 3, I convert from moles of product to grams of product, and then there's my final answer, 0.600 grams of water. So again, you don't need those intermediate values, right? You can just write it all in one line, as I'll show you in the next example, but you'll just calculate the last value. So just like any conversion, right, as we set it up, as long as we can cross-cancel our units as we go across, then everything should work out fine. So in this next slide, it's just an already solved problem, but then I'll do another example for you as well. So let's take a look at that. So here's my balanced equation. Sodium carbonate plus calcium chloride makes 2 sodium chloride plus calcium carbonate. So then in this set, what I want to do is, it's asking me how many grams of sodium chloride would be produced starting from 8.35 grams of sodium carbonate. So those are the things that I'm focused on here, right? So sodium carbonate is my reactant and sodium chloride as my product. So just like in any conversion problem, I can make a flow chart of what I'm trying to do. And it's going to be grams of grams of sodium carbonate, right? To moles of sodium carbonate to moles of sodium chloride to, ran out of room there a little bit, grams of sodium chloride. So those are the 3 steps, just like we saw in the flow chart, right? So for steps 1 and 3, I need the molar mass values for my reactant and product. And then for step 2, I just need to interpret the balanced equation and use the coefficients. So there will be problems that come up in the class where I'll suggest a couple different options in terms of how you can approach solving a problem. But then there'll be some where I just say, look, this is the best way to do it. I don't recommend trying any other method. That's what I would say for theoretical yield problems, right? Don't try to combine steps together. Don't try to skip steps. Every theoretical yield problem, no matter what's going on with the balanced equation, you should have these 3 conversion steps every time. I strongly discourage you from trying to combine things together. Otherwise, it gets fairly confusing. And one other thing to note is step 2 is the only point in the process where I even need to consider the coefficients in the balanced equation. it's not going to affect steps 1 and 3. Those are always going to be just the molar mass of the reactant and product. It doesn't matter what the coefficients are. So again, right, I'm showing you the finished PDF. If you're following the PowerPoint, it'll kind of pop through this equation. But if we're just following along, right, we start with our grams of sodium carbonate, then 1 mole of sodium carbonate divided by the molar mass, just figured out from totaling it up from the periodic table. So that's going to cancel, right? Grams of sodium carbonate with grams of sodium carbonate. And then now I'm in moles of reactant up here, right? Then in my next conversion, it's 2 moles of sodium chloride per 1 mole of sodium carbonate. So now moles of sodium carbonate cancel. And then in the last step, we want to get from moles of product to grams of product. So now moles of sodium chloride cancel with moles of sodium chloride, and I'm left with grams of sodium chloride. When I multiply this all across, I get 9.21 grams of sodium chloride. So same idea here, right? I'm going to round all my atomic and molecular masses to 2 decimal places. So then what's going to dictate my number of significant figures will just be the number of significant figures I start with that I'm given in the problem. So I was given 3 digits of accuracy for the grams of reactant, so I'm reporting 3 digits of accuracy for grams of the product. So that's how that one goes. All right, so I know it's not ideal to look at these slides where I've already shown you everything that's on there. It just makes it easier for me to mark everything, but we'll solve the next one from scratch, so that'll give you an opportunity to kind of see how it all goes. Hopefully it's already starting to make sense, but in the next slide we'll solve one from scratch. Okay, so same reaction, slightly different question. Now it's saying from 6.15 grams of calcium chloride, how many grams of sodium chloride am I going to make? So I kind of need to collect my information here. So let me get my calcium chloride molar mass real quick. So we need our reactant, calcium chloride. That's 40.08 plus 2 times 35.45. I think that's 110.98. Let me double check. Yeah, 110.98. And sodium chloride, that's 22.99, because it's from the previous slide anyway, plus 35.45, so that's 58.44 grams per mole. All right, so that's all the information I need, right? Because other than that, it's 1 calcium chloride makes 2 sodium chlorides. So now I'm ready to go. And so it's going to be grams of calcium chloride to moles of calcium chloride to moles of sodium chloride to grams of sodium chloride. All right, so we can figure that out. I'm given 6.15 grams of calcium chloride, and I want to convert that into moles. So moles will go in the numerator, right? 1 mole calcium chloride, 110.98 grams calcium chloride. So we know we're off to the correct start because grams of reactant have canceled out. Now we need to communicate with the balanced equation, which says 1 mole of calcium chloride in, 2 moles of sodium chloride out. So now moles of reactant cancel. You may see in my answer keys to the problem sets that I'll put a box around this step, just indicating that's the one and only place where I need to communicate with the balanced equation, and I've successfully done that. Okay, then lastly, 1 mole sodium chloride, 58.44 grams sodium chloride. So moles of product cancel with moles of product. We can verify down here that I've done everything, my 3 conversions, and we're left with the units that we want, so that's good. Let me just write the answer here. There's a little more space. So let me follow that across. 6.15 divided by 110.98 times 2 times 58.44. Rounded to 3 total significant figures, this will be 6.48 grams of sodium chloride. So that's my final answer for that problem. So just as a note to be aware of, right, we're talking about one reactant amount and asking about one product amount. When we're being given that one reactant amount, we're assuming that the other reactant has a sufficient amount to react completely with what we have, and that's how we know that it's going to go until we run out of this reactant. All right, so you should have plenty of practice on these with the problem set and the 101 homework. Hopefully it's making okay sense after having seen it a couple times. Again, I'll just say, like I said before, there's not really any shortcut to doing these. You're going to need to follow those 3 steps through every time. So I think I introduced these problems as theoretical yield problems in the beginning. So we can think about theoretical yield really as the maximum amount of product that can be made. So essentially to say, in the perfect world, if every bit of reactant gets converted to product, how much product am I going to form? So whenever we talk about theoretical yield, we're describing the value that we calculate in this type of equation. And that's different from the actual yield, which is the amount that we actually produce when we run the reaction in the lab. So some reactions just are never going to go 100% to completion. That's just the nature of the reaction. Also, when you're conducting an experiment in the lab, you may not convert all of your reactant to product because you might not recover all the product, or you might not let the reaction run long enough. It could be all sorts of things that would be causing that. So then in lecture, the way that we can work between actual yield and theoretical yield is really just that I'll give you an equation and make up a yield value for it and just say, hey, this is the equation. Tell me the theoretical yield. Here, given that this is the actual yield, can you report what we call the percent yield? And percent yield is just comparing the amount you actually got, the actual yield, to the theoretical yield. So think about it as a measure of efficiency, right? What I actually got divided by what I should have gotten, and then always times 100% to make it a percentage. So in reality, this should never be bigger than 100%, right? I shouldn't make more than I actually set out to make. But sometimes, like if your sample doesn't dry out completely, or there's just excess stuff that didn't get washed away, usually it's because it didn't dry out completely, you might get a percent yield above 100, but in normal conditions that shouldn't happen. If you completely dry your product, then you shouldn't get a percent yield above 100. So, like I said, since we're not actually doing any experiments in the lab, the way that I would incorporate actual yield into a problem is I just kind of make up a number that is smaller than what I know to be the theoretical yield, just to give you practice calculating the percent yield. Okay, so we're back to the same equation, right? Sodium carbonate plus calcium chloride makes 2 sodium chlorides plus calcium carbonate, and given an amount of sodium carbonate, we want to figure out the amount of sodium chloride that's going to be produced, and then in the follow-up question, it's giving us an actual yield amount and asking us to figure out the percent yield. So let's start with the top problem here. So 14.8 grams sodium carbonate. If I go back to the original example, it has the molar mass for sodium carbonate there and the mass of sodium chloride, which we've used a couple times. So I'm just going to use that value. So it will be times 1 mole sodium carbonate over 105.99 grams sodium carbonate. And again, for every 1 mole of sodium carbonate in, we get 2 moles of sodium chloride out. Remember, I told you you may see me put a box around this step just to indicate that is the one and only point where we're communicating with the balanced equation. Grams of reactant goes with grams of reactant, moles of reactant with moles of reactant. And so then in the last step here, 1 mole of sodium chloride equals 58.44 grams of sodium chloride. All right, looks like I made it work there in that space. So moles of product cancel. We're left with grams of product. And let's see what we get here. To 3 significant figures, I got 16.3 grams of sodium chloride. Okay, so now you've kind of seen the theoretical yield calculation happen 3 different times. Hopefully it's making sense how we're going through the steps in order to do that. Like I said, there's plenty more practice in the problem set and in the 101 homework to help you make sense of what's going on. But now you may see why we spent so much time early on working on those unit conversions, because it effectively works the same way. Okay, so now we've been given this fictitious actual yield, which I just picked a number smaller than what I knew the answer was to the previous part, just to practice calculating the percent yield. So if we go back, right, percent yield is actual yield divided by theoretical yield times 100%. We have those values now, so we can go ahead and do that. So the percent yield equals 15.2 grams divided by 16.3 grams. So what I actually got divided by what I theoretically should have gotten times 100%. Okay, 15.2 divided by 16.3 times 100, 93.251, so we'll call it 93.3%. So pretty good, right? Fairly close to the theoretical value that we wanted. All right, so looks like there's 9 or 10 slides left. That goes into a variation on theoretical yield problems. So I think I'll stop here and then we'll make one more video to wrap up this set of slides.